Well, welcome, folks. This is Mr. Bergman.
And I'm Mr. Sampson.
Mr. S is here.
We're back again for some KSP.
KSP. KSP is kind of a cool topic, don't you think, Mr. Sams?
Do.
KSP.
Ooh, nice black screen.
Black screen, yeah. You know, but before we talk about KSP, I've heard there's rumors that somehow you are the only student in your high school to get an injury during speech and debate.
Yeah.
I got to hear the story.
Yeah. Okay, so
all right, this is
we're out of town because I grew up in Wyoming, so we had to usually go overnight for these things. So went out on a Friday evening, stayed in a hotel. So it was me and two other guys staying in a hotel room, and we called down to the desk for a wake-up call at 6:30 because we had to be on the bus by 7. So, you know, 3 guys, doesn't take you very long to get ready.
Got it. All right, I'm there.
Never got the wake-up call.
No wake-up call.
So, at 6:58, there's a knock on our door, and it's our coach saying, "Hey, where are you guys? Let's get going." So we're going, oh, great, what do we do? So we're throwing on clothes, throwing things in our bags, just grabbing anything we possibly can just to get out the door in 2 minutes. So I have all my stuff. I've got a bag and another bag, and I'm running down the stairs in this hotel. So big old flight of stairs, and I have my dress shoes on, of course, and I slip. And about, I don't know, probably 10 stairs from the bottom. And, of course, I'm moving forward very quickly, so it's either fall flat on my face or try to land on my feet. Well, I tried to land on my feet, and I landed on one foot.
One foot.
And I landed on the side of that foot and rolled that foot, rolled that ankle, and heard a pop and some excruciating pain. Yeah, exactly. And so they got everybody else to the meet. They took me to the emergency room, had it x-rayed, make sure it wasn't broken. It was not. It was merely sprained, and I still made it back to the meet for my rounds, and I took second place in the tournament.
You got second place in your tournament, even with the bum ankle.
Yes.
And you had a speech and debate injury.
That is my speech and debate injury.
That is your story, and it sounds like you're sticking to it.
I'm sticking to it.
All right. Well, I guess we
never got the wake-up call.
Never got the wake-up call. Blame it on somebody else. That's usually a high school thing, I know. Yeah. Yeah, I didn't. I lost my homework. I lost my podcast. My iPod froze. Yeah. Okay.
Your podcasts crash my computer. No, they don't.
Yeah, they can happen. Okay. We're going to spend some more time. What's KSP stand for? Let's remind ourselves, or our kiddos here.
K is the equilibrium constant. And SP is the solubility product.
And product, of course, means multiplication. It does not mean like the product of a chemical reaction, so don't get that confused here. We're just going to run through a bunch more examples.
Yep.
The first one is I like to call the silly hydroxides. They are very silly. Why are hydroxides silly?
Well, there's hydroxides in there, but there's also hydroxides in water.
Yeah, see, we have a particular issue. Is that, of course, if I have iron 3 hydroxide, of course we know that to be FeOH3. And the way we've been doing this previously, this breaks up into Fe3 positives plus 3 hydroxides.
Yep.
But really, it always assumes that you're in an aqueous solution.
Yeah.
And what's that mean, aqueous?
That means you're dissolved in water. And if you're dissolved in water, water does this weird thing called autoionization. And it splits up into H plus and OH minus. So, not only do you have hydroxides from the iron 3 hydroxides, but you also have hydroxides in comparatively a fairly substantial amount from the water. Because the K values of these things are so tiny, water actually ends up contributing.
So normally we would say, if this was a regular problem that did not have a hydroxide in it, is you would say this is S and 3S.
Right.
But because the hydroxide is in water, you would say 3S plus
1 times 10 to the negative 7, because that is the concentration of hydroxide ions in water.
Yeah. Now it will change with pH. We'll talk about that in a little bit.
Yeah.
But so now we just simply plug this into our equation.
Yep.
Of course, the KSP would be equal to the concentration of the iron, 3 positive, times the concentration of the hydroxide cubed because of the 3.
Yep.
So this would be, what is the KSP of iron?
4 times 10 to the negative 38.
Pretty small number.
Pretty tiny.
And that would be equal to S times, now watch this, 3S plus 1 times 10 to the minus 7th cubed. Now you just have to just plug this into your solver and solve for S. The molar solubility, by the way, folks, is always simply S. It is the individual S.
Yep.
Not the 3S, not the 2S, what have you. They're asking just for what is S. Some people like to use X or whatever, but it's essentially the same thing. So what do you get, Mr. Sampson, solve for S?
I'm frantically putting it into my calculator. Is that a third power?
That is cubed.
Yes, that is a cube. Okay, it looked kind of like a 7 there.
Yeah, sorry.
So that's
My handwriting could be better.
Bye.
A trace, it is a 3 Don't you think? I think it's a 3, says Mr. Mole. Okay, he's still frantically getting his calculator solver.
Clicking away. Oh, something happened in my solver.
All right, I'm going to push pause while Mr. Solver.
Times 3x.
You know, to solve this, let's talk yourself through the solving of this one, is I would take x, because this is on my solver and my calculator, parentheses, 3x. You have to use x's in the calculator, right? Plus 1e, not plus, yeah, plus 1e, negative 7, parentheses, caret 3, minus 4.3, what was our number?
It was 4 times 10 to the negative 38.
4.0 e negative 38. And that set that essentially equal to 0. So I think it should look like that. And then you're going to choose an x that's very, in terms of a guess, choose the x. It's going to be an itty bitty number, I'm pretty sure. So I just like, you know, as a guess now.
I'm using
0.00001 or some number like that. Make a really, really small guess, and then you can solve for
There we go.
S.
Now I have a number.
And so what do you get for S,
I got
Mr.
4.0 times 10 to the negative 17.
So the molarity is 4 times 10 to the minus 17th moles per liter, the molar solubility.
Yep.
Again, what does that mean? That means if I had a beaker filled with iron 3 hydroxide, which would actually be, you know, the iron 3 hydroxide would be a powder that would set to the bottom, and the Fe plus 3 and the OH minus would dissolve to the extent of that number. It was 4 times 10 to the minus 17th molar. So that's essentially what that means.
Yep.
Okay? All right. Now, you know, we should do one more thing on this, guys. So let's just add one more thing. So what happens, do I have a problem like that in the future, Mr. Sams, about if we had a different pH?
I don't
Let's take this same problem, and let's say the pH was equal to 5. So the question was, what is the molar solubility? So let's add a question to this question. What is the molar solubility of the iron 3 hydroxide if the pH is equal to 5?
Okay.
So what you would do, again, you Fe, OH3, again, dissociates into irons plus 3 hydroxides. Now, if you know the pH is 5, what do you know?
That your pOH is 9.
So what does that mean? What else? How is that going to relate to this particular problem?
Well, instead of the hydroxide concentration being 1 times 10 to the negative 7, it's going to be 1 times 10 to the negative 9.
And actually, this is confusing to students because that actually is the concentration. It's not 3s plus that. It just is 1 times 10 to the minus 9th when you say that's your pH. So you would say this is S, and this is 1 times 10 to the minus 9th. So when you solve your problem, you'd use your KSP expression, which was, what was it, 4 to the minus 38?
4 times 10 to the negative 38, yeah.
4 times 10 to the minus 38. And you say that equals S times 1 times 10 to the minus 9th. And of course, you still have to cube it because there still is this 3 right here. And then you just simply solve for S. You just divide by 1e to the minus 9th cubed, and you get the molar solubility here. Probably a much higher number than our previous number. What do you get?
4 times 10 to the negative 11.
So by changing the pH, by lowering the pH, because you lower the pH, you have more hydrogens, which will then, essentially, when you add hydrogens, think of this from a Le Chatelier's principle. If I add hydrogens, what does that do?
Shifts the equilibrium to the right because we're taking the hydroxides away.
And so then, if this is 10 to the minus 11th, though a very small number, no question.
It's still considerably bigger than...
I think we're 10 to the minus 17.
10 to the negative 17, yeah.
Yeah, so compared to 10 to the minus 17th, you're 6 factors. That's, what, 100,000? 100,000 times more soluble when you increase the pH. And if we were to go like pH of 4, you'd do the same thing, and this would be like, you know, you change this number, and you could actually, I actually know that you could make this soluble in water in a very low pH system, like, you know, pH of 2 or something. I don't know, we could do the math, but we don't start. So watch that, is if they give you the pH, they're giving you the entire hydroxide concentration.
Yep.
All right, change gears a little bit. There's always a typical question, or not always, very often I should say, a typical question in the AP exam, but also just a typical KSP question is, will there be a precipitate form? So if you mix two solutions, so if I have a beaker of one chemical, and I pour it into a beaker of another chemical, there we go. I pour them into a beaker, will they make a precipitate? And there's this concept called the QSP. So if the QSP is greater than the KSP, then yes, you will make a precipitate. And if the QSP is less than, then the answer is no. Now, what in the world is a QSP?
Yeah, that's, what does the Q stand for? I can't remember.
It's the
Quotient,
quotient, I think, is what, yeah, it does. The QSP is essentially kind of like equal to the KSP, but not in terms of value, in terms of expression.
Right. And the Q comes from your initial values prior to an equilibrium shift.
You'll see, it's probably easiest to do our example. So will a precipitate form? So here we have a situation where we have a beaker of sodium phosphate. Okay, so in beaker number 1, I have sodium phosphate, or sodiums and phosphates, right? And in beaker number 2, and actually I've got some numbers on here. This is 0.00025 molar, the phosphate is. And then the sodium is triple of that. That's kind of confusing. And then you got barium chloride, Ba positive 2 and chloride minus. Now if you were to think this from a double replacement perspective, it'd be Na3PO4 plus BaCl2. Now if you know your solubility rules, of course you make salt, but what do you know about salt?
That's soluble.
It's soluble because it's one of our NaCl-nosos. It's NaCl, right?
Yeah.
And plus barium phosphate, Ba3PO4 Now we have memorized that to be insoluble, right?
Yep.
It's not a NaCl-noso, so to speak. And so therefore that creates an issue. So the question is, when you pour these together, will the concentration be high enough? So what we need to do is to kind of figure out what are our concentrations when we pour them together, because we have 50 milliliters of one and 50 milliliters of the other.
Yep.
I like it when you pour equal volumes together. When you pour equal volume, what happens to the concentration?
Just cut it in half.
Yeah, PO4 3 negative. Technically, we're actually using the equation M1V1 equals M2V2. But if the volume of 1 is 50 and the volume of 2 is 100, then when you do that, you cut your molarity in half.
Yeah.
So the concentration of the phosphate, that's what we care about here from this first one, is 0.0025. So if I just divide that by 2, I get
1.25 times 10 to the negative 4.
Yeah, let's put an exponent.
1.25
times 10 to the minus 4th molar.
Yep.
And the other one I'm going to care about is the barium. You're going to see how this works in just a second. I think you're probably a little confused. You take the barium concentration, which was 0025, and you divide that by 2, and you're going to get 1.25 to my third, maybe?
Yep.
Okay. Because you see, essentially what we've got is we've got barium Ba3, PO4, 2. Now I know in this previous thing is that we had this as a product of the reaction.
Right.
But what I need to do is need to write it in a KSP expression, so I just break it apart, just like we've been doing ever since we started this KSP business. So I am doing that right now, as you can see on the screen. But what do I know? You see, I know the phosphate concentration is this number, and the barium concentration is this number. So we know the numbers.
Yep.
Now, if these were the real numbers, then you'd multiply and get the KSP, but that's not actually how it works.
Right.
These are the concentrations, and if we multiply these together, taking into considerations the cubed on the barium and the squared on the phosphate, then I can find the what's called the QSP.
Right. These are not equilibrium concentrations. These are concentrations when it's initially mixed.
When they just mix them.
Right.
Exactly.
Before it does any equilibrium.
Concentration.
Right.
So now I'm going to say the QSP would be equal to the barium concentration, which is 1.25 times 10 to the minus third, and I'm going to cube that, of course because of the 3 here, times the phosphate concentration, 1.25 times 10 to the minus fourth, and I'm going to square that. And I come up with what number, Mr. Sims?
3.05 times 10 to the negative 18.
Now, what we now need to look up on the table is the actual value of the KSP. So we're looking in the table in the back of your book.
6.
Or, you could look, we have this table right here in our podcast, so you've got that somewhere in your notes. So what is it, Mr. Sims?
It says 6 times 10 to the negative 39.
So the real value is 6.0 times 10 to the minus 39th. So now we compare our two numbers. The QSP, 10 to the minus 18th, the KSP, 10 to the minus 39th. Which number is bigger?
The Q number is bigger.
So that means, guess what? You will
not
make a precipitate. No, yeah. If QSP is greater than the KSP,
oh, it is greater. Sorry, my
precipitate.
brain went the wrong direction.
Yeah, and so you got to watch that. Careful. If QSP is greater than the KSP, then yes, we make a precipitate. If this number had been not 10 to the minus 18th, but 10 to the minus 30 or 40th or something like that, then of course you would not have made a precipitate. You would have not crossed the appropriate threshold. Okay, next question. All right, these are the hardest questions in all of KSP, in my particular perspective, where we have competing precipitates.
Oh, yeah.
Which precipitate will form? Because sometimes we have I like to call this the competing precipitate problems. Okay, so we've got sodium chloride. We need to kind of draw a picture, or just box. This is our beaker. So let's try and figure out what we've got. Sodium chloride. So we've got sodiums and chlorides. They dissociate it, right? And the mixture contains lead to nitrate, right?
Yep.
And silver nitrate. So we got like all kinds of things. But who's kind of going to make something happen here, Mr. Sams?
Well, the chloride could go with the lead, and it could also go with the silver to make a precipitate on either one of those, because both of those are exceptions to our Knuckle-Nusso rule.
So first, the na and the nose go away. So we have three things that can get together, because if you recall, all chlorides are solid with the exception of lead-2, so it'd be PbCl2, or silver. So both of these are precipitates from our memory list, right? And so which of these will form, and it has to do with the concentrations and the KSPs and all that kind of stuff.
And the Q in this case.
And the Q in this case. So what you do is you have to, I like to, if I'm going to do competing, I'm going to take your paper and kind of divide by 2. I'm going to do PbCl2. I'm going to write the KSP expression for each of these. Pb2 positive plus 2 chlorides. And on this side, I'll say AgCl breaks apart into Ag positive and Cl negative. So write this out, and now we're going to go back to our problem, and we're going to get some numbers here. What do I know about each of these numbers?
We've got a 50 milliliter beaker, and it's 0.00015 molar lead to nitrate.
So that's the lead-2. We forget the nitrate. So if I go back here, the lead-2 here is 0.00015 molar.
Yep.
And then the silver, we go back and we find that number, 00035 on that one. The silver was 0.0030?
3 zeros.
035. So this breaks apart into leads and then to S for the chlorides. And this is going to break apart into S.
Yep.
And so if you were to write the KSP expression, the KSP, I'll try and write small here so we can, is the lead, 2 positive, times the chloride, in this case, squared. But what I'm going to do is I'm going to try and solve for S. Now the KSP of lead to chloride from the book.
1.6 times 10 to the negative 5. By the way, guys, I'm looking at my book and I'm looking at that table we gave you earlier. The numbers tend to be different. In the book it says values at 25 degrees Celsius. And as we know, the K values can be different at different temps. The table that's in your handout is probably at a different temperature. It just doesn't seem to be labeled as what temperature. But that's why it's different than the ones in the book.
Yeah, I got that off of the internet and Wikipedia, I think, actually.
Pesky internet.
Yeah. All right, so you would solve for this. So what did you get here, Mr. Sams?
Sorry, I'm too busy talking.
Now, again, a warning on this particular problem here. When I have 2s squared, that's really 4s squared because it's the quantity 2s squared. It's 2s squared, not 2s squared.
All right, I have 0.163.
So the molarity, okay, well, let's get the two numbers and we'll talk about what they mean. For this one, of course, we'll say that the KSP is equal to the Ag positive times the Cl negative. So the KSP of silver chloride is
1.6 times 10 to the negative 10.
Times 10 to the minus 10. Much smaller number, but we have a different sort of factor. We don't have to square anything.
Right.
So 0.00035 times S. I think we're going to get a small number on this one.
We are. This one is 4.57 times 10 to the negative 7.
So now I want us to sort of envision this. What you've got is you've got a beaker that contains lead ions and silver ions. It's also got the sodiums and the nitrates, but we don't care. And now you're essentially titrating, you know, from maybe a burette or something like that. You're titrating in here the chloride ions. When they come in here, they can be they are attracted to both the lead and the silver. Which one is going to form first? Well, when the concentration of the chloride reaches 4.57 times 10 to the minus 7th, you will make AgCl. When the concentration of the chloride reaches 0.163, you'll make lead chloride. Well, which one will form first then?
The silver one, because it's way smaller. You're going to hit that concentration very, very early.
So once the concentration reaches that 4 number, 4.57 times 10 to the minus whatever it was, 6th or 7th? 7th. That's when you'll start making the silver. The lead is not going to form until you get it to 0.163. So therefore, the silver will form first. All right, the silver chloride will form first. Okay. All right. Example 7. All right, this is, well, I said the last one was the hardest problem, and I lied. This one is a competing precipitate and then with a percentage. Yeah, this was an old question on the AP exam a long time ago, and this is a nasty one. Okay, at 25 we have the KSP for strontium sulfate. Okay, what is the molar solubility of the strontium sulfate in pure water? Actually, this is a relatively easy question. Okay, so we know strontium sulfate, so Sr, SO4. All right, sorry, we had an interruption there. So strontium sulfate dissociates into Sr2 positive plus the sulfate 2 minus. And it's just finding, it's the question, what's the molar solubility?
Yep.
This is an easy question.
This is solving for X.
This is solving for S.
Oh, sorry, S.
S, it breaks into S and S, right?
Yep.
So the value of strontium sulfate they gave this to us in the problem was 7.6 times 10 to the minus 7th. That equals S squared. You just take the square root, don't you, Mr.
Yep.
Sams? So S equals
8.7 times 10 to the negative 4.
times 10 to the minus 4th molar, and that is the molar solubility of the strontium sulfate.
Yeah.
So actually, let me just make a quick note about these particular types of problems. If you get a problem, an AP problem, usually question A is a softball.
Yeah.
Easy smeezy. Okay, now B, C, D, yeah,
maybe
maybe not so easy.
So
In fact, I think like D on this one is a bugger.
And you often have to use the answer for A in the rest of the problem, so don't screw that one up.
Yeah, well, and another thing, though, if you do screw that up, and you know that the answer and know how to solve part, say, C,
Yeah.
and you need the answer from part B, write this word. Write assume the answer to B is, make up a number. How about 1 times
Yeah.
10 to the minus 4th molar, or something like that.
If you do it right with the wrong number, you'll still get credit. Now, granted, you'll make your grader really cranky, and you better hope it's not Friday afternoon at 4:58 when they're grading it, but they're supposed to give you credit for it.
Because you see what he has to do is he has to punch into his calculator. That's calculator.
Yes.
You noticed that, right?
Yes, and they'll be cursing you the whole time.
Because they have to actually run with your assumed number, your numbers through, to see if you got the answer correct based upon that.
Yep.
So you can do that, and that's how we will grade your exams as well. That's
Yep.
how we always have. All right. Okay, so this is part A, of course, and again, a commentation that this is a relatively easy part. So let's now look at part B.
Also, relatively easy.
Yeah, this one's not terribly difficult. It says, what is the molar solubility? Now, what's that asking for?
Well, basically, we're solving for S.
Yeah, just what's S is all they're asking for. Sulfur, strontium fluoride. So
Yep.
you'd say Sr, F2 dissociates into Sr2 positive and 2 fluorides. So that'll break apart into S and 2S. So, and then the KSP for strontium fluoride.
7.9 times 10 to the negative 10. That's given in the problem.
This was given in the problem. Now, you've got to make sure you realize that, what's given in the problem. So this is the S times the quantity 2S squared. Now, this is going to come out to, I like to just think this through, 2 squared is 4, and then S squared times S, this is 4S cubed. So divide by 4,
Yep.
and take the cubed root, or take it to the 1/3 power. S is equal
power.
to
5.8 times 10 to the negative 4.
5.8, 10 minus 4 molarity. That's your answer, folks. Indeed, indeed. All right, hey, A and B weren't too bad. Were they,
No,
Mr.
those are
Sims?
easy. Don't mess those up.
That's pretty easy. Now
Yep.
C. Oh, man. Which salt precipitates first? Now, we did a problem like this a
We
little bit
just
ago.
did, yeah.
Yeah. Okay, so this is just one of those ones where we say, all right, which one? This is where you've got the beaker.
Yep.
All right. All right, now what have we got here? We've got in, let's think this through. We've got strontium nitrate is added slowly. Now, what we care about in the strontium nitrate being added slowly is the strontium plus 2. And what's down in the beaker is some fluorides and some sulfates.
Now, just remember that we just determined the molar solubility of strontium sulfate and strontium fluoride.
And the
So we've done work with
fluoride
those.
is 0.10, and the sulfate, pardon me, I did that backwards.
Nope.
The
Yep.
fluoride is 0.02 molar, and the sulfate is 0.10 molar. All right. Now, by the way, this is strontium sulfate. I should just make a note. Strontium sulfate. Is that one of our exceptions, Mr. Sams?
It is.
It is. I'm not sure we have that in their memory list. All sulfates are
Actually, I think it
soluble. It's
was.
like barium, oh yeah, it's barium, strontium related. And this is one of those exceptions. Okay. So the question is, which is going to precipitate first?
Yep.
Remember, we like to set this up in a 2-column type of a deal. I'll do the strontium fluoride here, and that dissociates into strontium, 2 positive, and 2 fluorides. And then conversely, strontium sulfate dissociates into strontium, 2 positive, and sulfate. And now we know something about our fluoride and our sulfate.
Yes, the fluoride is 0.020 molar.
0.020 molar. And the
sulfate is 0.10.
0.10. All right. Now, essentially what we're going to do is we're going to solve for the strontium concentration, or S, the molar solubility. So our KSP of strontium fluoride.
Strontium fluoride, KSP 7.9 times 10 to the negative 10.
And that will be equal to S times 0.020 squared. Now you do have to square it because of this. And so the solubility, or the concentration of the strontium, really, this is actually the concentration of the strontium when the precipitate forms. When you just do the math, you take 7.9 times 10 to the minus 10 divided by 0.02 squared, and you get
1.975 times 10 to the negative 6. So you could call it 2.0, I suppose.
All right, and then this one, we'll say, what's the KSP of strontium
7.6 times 10 to the negative 10. Sorry.
7.6.
No, negative 7. 7.6 times 10 to the negative 7.
Wahuda! 7.6
times 10 to the negative 7. That's given in the problem.
Okay, equals S times 0.10. And this will be the first power, because there's a 1 right there, implied. So you just divide by 0.1. That's 7.6 to the minus 6, right?
Yep.
7.6 times 10 to the minus 6 molar. And that's the concentration of the strontium when it starts to precipitate.
Right.
So which one wins?
The one that is smallest wins.
No, I think it's the highest one.
Is it the highest?
No, it's the smallest.
It's the smallest, yeah.
Yes, you see, because in 1.98, or essentially 2, is smaller than, and they're both 10 to the minus 6, right?
Yep.
So the smallest one, because let's think back to the picture again.
Yeah, as we add the strontium nitrate into it, we're going to hit that lower concentration first, causing the one with the lower S value to precipitate out first.
So you're going to make F2, and you'll make this first.
Yep.
Is that the right one? Did I pick the right one?
Yep.
I'm sorry, I forget.
That's right.
Yeah, the strontium fluoride, because it's going to precipitate when it's roughly 2 times 10 to the minus 6 molar, and the strontium sulfate when it's 7 times 10 to the minus 6-ish, it's going to start precipitating. So it's a simple answer. Now, it's not simple. You have to actually say the SRF2 precipitates first and then because the concentration of the strontium is lower. Because I think it asks you to justify the answer.
This one actually doesn't, but it just says which salt precipitates first.
Okay, but you have to show the work.
Show
if
your
you didn't
work.
show the work, you wouldn't get the points.
No.
Okay.
But if you're completely clueless, you can at least guess.
Now,
might get something.
I think this question is somewhat confusing, but it's not horrid if you think it through. What is the concentration of the strontium ion in the solution when the first precipitate begins to form?
We just solved that.
I was thinking of the next problem, probably.
This
is easy.
Yeah.
Actually, I almost think you need to answer this problem first before you can answer which precipitates first.
Right.
And of course, that answer is
1.98 times 10 to the negative 6.
So 1.98 times 10 minus 6 molar. That's pretty easy, isn't it?
Yeah, and there may be some other way to solve it that goes another order or something.
All right.
But
as more strontium nitrate is added to the mixture, a second precipitate forms. At that stage, what's the percent of the anion of...
Anion of...
the anion, I think this through here. Hold on. Okay, way to figure this out. We're missing some words here. Of the first precipitate remains... So copy this down in your notes. In solution. Okay? So that's what it's supposed to say.
Yeah.
All right, sorry about that. Okay, now...
The first precipitate was the strontium fluoride.
So let's go back to this chart. It all comes back to this chart right here. Let's change colors here. Okay. The strontium fluoride was the first substance to precipitate. The second precipitate happens when this concentration reaches 7.6 times 10 to the minus 6.
Yes.
The question is, how much of the strontium sulfate of the 0.02 remains?
Fluoride, you mean?
But yeah, of the...
How much fluoride ions are left when the strontium sulfate starts to go?
Yeah, as a percentage.
Yeah.
And actually, this is not horribly difficult. What you have to do is that you have to take this. This is the concentration of the strontium. You're going to take this number and you're going to plug this into right here as your strontium concentration, and then you're going to solve for the fluoride concentration. This becomes X, if you will.
Yes.
And so let's do that. So you have to go back, and we're going to say 7.9 times 10 to the what is it?
Negative 10.
Negative 10. And that is going to equal, let me go back to that page, 7.6. 7.6 times 10 to the minus 6. Is it squared? I think it is. Yes. Times X squared. Now where X is the concentration of the fluoride when the concentration of the strontium reaches this, so you divide by 7.6 and take the square root, and you get
0.010.
0.010. Now this is pretty easy because the original concentration of the fluoride, so the F negative, say, original, as I recall, was 0.020.
Yes.
Well, 0.010 divided by 0.020 times 100 is not hard math, folks. That is a 50% deal.
50%, yep.
So 50% of it has been reacted away. All right? Okay, I think we are almost done.
I think...
More examples. I don't know. Do we need to do more examples?
I think we're probably pretty good there.
I think we're happy campers. So I think that is done. So don't forget to ask Mr. Sams more details about the
speech and debate injury.
Speech and debate injury. I'll bet there's more to that story he hasn't told you.
That's most of it.
Probably so. Okay, we will see you in class, or email us via internet land stuff. Bye.
Bye.